The Secret Code, an introduction to cryptography. Cryptography. The word itself sounds like something out of a spy movie, and in a way, it is. Cryptography is the art of writing and solving codes, of hiding information in plain sight. It's the invisible shield that protects our digital lives from online banking to private messages. Imagine sending a postcard with your deepest secrets written on it for all to see. That's what it's like sending information online without encryption. Cryptography is the envelope that protects your message, transforming it into an unreadable jumble for anyone without the key. Throughout history, humans have used codes and ciphers to protect sensitive information. From the Caesar cipher used by Roman emperors to the Enigma machine that confounded codebreakers in World War II, cryptography has played a pivotal role in shaping our world. Today, in the digital age, cryptography is more important than ever. It's the bedrock of our online security, ensuring that our data remains confidential and tamper-proof. Without it, our digital lives would be as vulnerable as that postcard, open for anyone to intercept and read. Two keys to the kingdom's symmetric and asymmetric encryption. These two methods are the backbone of secure communication in our digital world. Imagine a locked box where you want to store a secret message. This box represents the data you want to protect. You have the key and you share a copy with your trusted friend. This key is crucial because it allows both of you to access the contents of the box. This is the essence of symmetric encryption. It's like having a master key that both parties use to lock and unlock the box. You use the same key to lock, encrypt the message, and your friend uses the same key to unlock, decrypt it. It's simple and efficient, making it ideal for situations where speed and simplicity are paramount. Now imagine a different scenario. What if you want to communicate securely with multiple people without sharing your key with everyone? You want anyone to be able to send you a secret message, but you don't want to share your key with everyone. This is where the complexity of secure communication increases. This is where asymmetric encryption comes in. It introduces a pair of keys, one public and one private, to solve this problem. It uses two keys, a public key that anyone can use to encrypt a message for you, and a private key that only you possess to decrypt it. This separation of keys ensures that your private key remains confidential. Think of it like a mailbox. The mailbox is accessible to everyone, but only you have the key to open it. The mailbox slot is your public key. Anyone can drop a letter in. This means anyone can send you an encrypted message. But only you have the private key, the mailbox key, to open the mailbox and read your mail. This ensures that only you can access the contents. Asymmetric encryption is the foundation of secure online communication, allowing us to share sensitive information without worrying about it falling into the wrong hands. It's used in various applications, from emails to secure websites. Asymmetric encryption might seem like magic, but it's based on complex mathematical principles. These principles ensure that the encryption is strong and reliable. It ensures that even if someone intercepts an encrypted message, they won't be able to read it without the private key. This makes it incredibly secure. This duality of keys is the genius of asymmetric encryption, providing a secure and elegant solution for confidential communication in the digital age. It allows us to maintain privacy and security in an increasingly connected world. The fingerprint of data hash functions and their magic. Imagine a special machine that takes any piece of information, no matter how big or small, and transforms it into a unique code of a fixed length. This transformation is both fascinating and crucial in the world of digital security. This code, called a hash, acts like a fingerprint for the data. Just as no two fingerprints are the same, no two hashes are identical for different pieces of data. Change even a single character in the original information, and the hash will change completely. This sensitivity to change is what makes hash functions so powerful and reliable. That's the power of hash functions. They ensure that even the smallest alteration in data is detected, making them indispensable in data security. They are one-way functions, meaning it's practically impossible to reverse the process and recreate the original data from the hash. This one-way nature is crucial for maintaining the security and integrity of the data. This property makes hash functions incredibly useful for ensuring data integrity. They act as a digital seal, guaranteeing that the data has not been altered. Think of it like verifying the authenticity of a document. By comparing hashes, you can confirm whether the document is genuine or has been tampered with. You can create a hash of the original document and compare it to the hash of a suspected copy. This comparison is quick and efficient, providing instant verification. If the hashes match, you can be confident that the document hasn't been tampered with. This method is widely used in various fields, from legal documents to software distribution. Hash functions provide a reliable way to detect even the slightest alteration in data. This makes them essential for maintaining the integrity of sensitive information. Hash functions are also used extensively in cryptography for password storage. They ensure that passwords are stored securely and are not easily accessible to unauthorized users. Instead of storing passwords in plain text, which is highly insecure, websites use hash functions to store the hash of the password. This adds an extra layer of security. When you log in, the website hashes the password you entered and compares it to the stored hash. This process ensures that only the correct password grants access. This way, even if the website's database is compromised, your actual password remains protected. Hash functions thus play a critical role in safeguarding personal and sensitive information in the digital age. Section 4. Linking the block's hash pointers in the blockchain. In the world of cryptocurrencies, there's a lot of talk about blockchains. These digital ledgers are the backbone of cryptocurrencies like Bitcoin and Ethereum, providing a secure and transparent way to record transactions. But what exactly are they, and how do they ensure the integrity of transactions? The answer lies in the ingenious use of hash pointers, a fundamental concept that underpins the entire blockchain structure. Hash pointers are not just regular pointers, they are pointers that also contain the hash of the data they point to. This dual functionality is what makes them so powerful. Imagine a chain of blocks, where each block contains a set of transactions. These blocks are linked together in a linear, chronological order. Each block also has a header that includes a hash pointer, which is simply a hash of the previous block's header. This hash pointer serves as a unique fingerprint for the block. This creates a tamper-proof chain of blocks, where each block is linked to the one before it. The integrity of the entire chain depends on the integrity of each individual block. Let's say someone tries to alter a transaction in a previous block. This would not go unnoticed. This alteration would change the block's hash, which in turn would change the hash pointer in the next block. The change would propagate through the entire chain. This domino effect would continue down the chain, making it immediately obvious that tampering had occurred. The entire network would be alerted to the discrepancy. This interconnectedness of blocks through hash pointers is what makes blockchains so secure. It ensures that any attempt to alter the data is easily detectable. Any attempt to alter the data in a block would require changing every subsequent block in the chain, which is practically impossible due to the computational power required. This immense computational requirement acts as a deterrent to tampering. Hash pointers are the invisible threads that hold the blockchain together, ensuring its integrity and immutability. They are the unsung heroes of blockchain technology. They are a testament to the power of cryptography in creating secure and transparent systems for recording and verifying transactions. Without hash pointers, the blockchain as we know it would not be possible. Section 5. The Tree of Trust, Merkle trees and data integrity. Imagine a large data set that needs to be verified for integrity. Checking each piece of data individually would be inefficient and time-consuming. This is where Merkle trees come in, providing an elegant solution for efficient data verification. A Merkle tree is a tree-like data structure where each leaf node represents a piece of data, and each non-leaf node represents the hash of its child nodes. The root node at the top of the tree represents the hash of the entire data set. This hierarchical structure allows for efficient verification of individual data pieces. Instead of checking the entire data set, you only need to check the path from the specific data piece to the root node. If the hashes match along the path, you can be confident that the data hasn't been tampered with. Merkle trees are widely used in peer-to-peer networks and distributed systems, including blockchains. They allow for efficient verification of large data sets without requiring each participant to download the entire data set. This makes them ideal for ensuring data integrity in decentralized environments where trust is paramount. Section 6. Signing on the digital line, digital signatures and ECDSA. In the physical world, we use signatures to verify the authenticity of documents and transactions. But how do we sign documents in the digital realm? Enter digital signatures, the cryptographic equivalent of a handwritten signature. A digital signature uses asymmetric encryption to bind a person's identity to a digital document. The signer uses their private key to create a digital signature, which can be verified by anyone with access to the signer's public key. This ensures that the signature is authentic and cannot be forged. One widely used algorithm for digital signatures is the elliptic curve digital signature algorithm, or ECDSA. ECDSA is known for its efficiency and security, making it suitable for resource-constrained environments like mobile devices and embedded systems. Digital signatures are used extensively in cryptocurrencies to authorize transactions. When you send cryptocurrency, you sign the transaction with your private key, proving that you authorized the transfer. This digital signature is then verified by the network to ensure the transaction's authenticity. Digital signatures are essential for building trust and security in the digital world. They provide a reliable way to verify the authenticity of digital documents and transactions, ensuring that they haven't been tampered with and that the purported sender is indeed who they claim to be.